Okay, so right now, inside your home, an invisible, highly flammable gas is flowing through a network of pipes directly beneath your living room floor and behind your bedroom drywall. Under the right conditions, just a single spark from a light switch or a static shock from your socks could instantly ignite that gas, triggering a violent explosion powerful enough to lift a two-story house clean off its foundation. Yet every single day, millions of people cook on open flames, take boiling hot showers, and heat their homes in sub-zero blizzards without a second thought. The only reason this invisible fuel keeps you comfortable instead of leveling your house is a series of precision-engineered pressure regulators, physical sediment traps, microscopic electrical safety circuits, and thermodynamic fail-safes. Here is how your house harnesses the explosive power of natural gas and propane from the street main all the way to your burner flame, completely safely from start to finish. To understand how this fuel behaves inside your walls, you first have to understand the strange physics of the gas itself. Pure natural gas, which is mostly methane, is completely colorless, tasteless, and odorless. If raw natural gas started leaking into your basement, you could walk right into a lethal cloud of explosive fuel and never know it was there until it was too late. Because of that terrifying hazard, utility companies inject a potent chemical odorant called Mercaptan into the gas stream long before it reaches your neighborhood. Mercaptan contains concentrated sulfur compounds that produce that unmistakable, pungent, rotten egg smell, and human biology is so remarkably tuned to it that your nose can pick up a leak when the gas concentration is as low as 1%, long before it reaches its explosive threshold of 5% in the air. Before that gas gets to your property, it travels through massive underground transmission lines and municipal distribution mains buried deep under your street. Inside those city pipes, the gas is compressed under serious pressure, often ranging from 10 to 60 pounds per square inch, or psi. If that high-pressure street gas were allowed to blast directly into your house, it would instantly blow out appliance valves, rupture burner gaskets, and cause catastrophic leaks. This is why the first and most critical gatekeeper on your property is the gas meter assembly and service regulator mounted just outside your exterior foundation wall. As that high-pressure gas surges in from the street supply line, it hits the service pressure regulator, a mechanical valve packed with a spring-loaded rubber diaphragm and a precision orifice. This regulator violently throttles the incoming pressure down from 60 psi to a gentle delivery pressure of roughly 1/4 of a pound per square inch, which in plumbing terms is measured as just 7 inches of water column. Right next to the regulator body is an atmospheric vent, designed to safely bleed excess gas into the outdoor air if the internal diaphragm ever tears. Directly beside the regulator sits the emergency main shutoff valve, a heavy quarter-turn brass valve with a rectangular metal tang. When that tang is aligned parallel with the pipe, gas flows freely into your home, but turning that tang 90 degrees perpendicular immediately cuts off the entire fuel supply to the house in less than 2 seconds. Once the gas passes through the utility meter, it enters your home's internal supply piping network. For over a century, the standard for indoor gas piping has been heavy Schedule 40 black iron pipe joined with threaded malleable iron fittings. Every single threaded connection on a black iron pipe is tapered, and technicians apply specialized gas-rated yellow Teflon tape or Teflon-infused pipe thread compound to fill microscopic imperfections in the threads, creating a gas-tight seal capable of holding hundreds of pounds of pressure without leaking. Now, in modern residential construction, contractors often use corrugated stainless steel tubing, commonly known as CSST. CSST is a flexible, yellow-jacketed stainless steel pipe that can be snaked through wall studs and floor joists like electrical wire, drastically cutting down on threaded joints and potential leak points. But because the stainless steel walls of CSST are relatively thin, electrical physics introduces a serious hidden danger. If lightning strikes near your house, the resulting electrical surge can jump between household metal and the CSST, arcing through the thin metal wall and burning a pinhole leak that feeds a continuous torch of burning gas inside your walls. To prevent that nightmare, building codes strictly require CSST systems to be directly bonded to the home's electrical grounding system with a thick copper conductor, safely redirecting lightning surges straight into the earth before an arc can form. Inside your basement or utility room, the main gas line splits into a manifold distribution hub, branching off into dedicated supply lines that feed each appliance, including your furnace, water heater, kitchen range, and clothes dryer. But before any of these pipes connect to a delicate gas valve, plumbers must install a crucial mechanical defense known as a sediment trap, or dirt leg. A sediment trap is a simple T-fitting where the gas enters from the top, makes a sharp 90-degree turn into the appliance, and drops heavy rust flakes, pipe shavings, or manufacturing debris straight down into a capped vertical pipe nipple at the bottom. Because gas is lightweight and easily whips around the turn, while solid debris has inertia and falls with gravity, the sediment trap keeps contaminants from ever lodging inside the precision rubber seats of your appliance valves. When gas reaches an appliance like your furnace, it encounters the electronic combination gas valve, which contains two redundant electromagnetic solenoid coils wired in series. When your thermostat calls for heat, the furnace control board checks multiple safety interlocks, including the draft inducer pressure switch, the high temperature limit switch, and rollout flame sensors. Only when every single safety switch confirms that conditions are safe does the control board send low voltage current to energize the solenoid coils, snapping the plungers upward and letting gas surge into the burner manifold. At the burner manifold, the gas enters individual burner tubes through tiny brass nozzles called orifices. As the high-velocity jet of gas shoots out of the nozzle into the burner tube, it creates a localized vacuum known as the Venturi effect, automatically sucking in ambient air through adjustable shutter openings and mixing oxygen with the raw gas in an exact ratio of roughly 10 parts air to 1 part natural gas. If this air-fuel mixture has too much air, the flame will lift off the burner and blow out. But if it has too little air, incomplete combustion occurs, producing a lazy, flickering yellow flame and dangerously generating high levels of toxic, odorless carbon monoxide gas. A healthy, perfectly balanced burner flame burns with a sharp, crisp, bright blue cone. To ignite this air-fuel mixture, older appliances used a continuous burning pilot light, but modern high-efficiency systems use electronic hot surface ignition. The control board sends line voltage current through a ceramic igniter made of silicon carbide or silicon nitride, heating the element to over 2,000 degrees Fahrenheit until it glows incandescent orange hot, instantly igniting the gas cloud as soon as the valve clicks open. Once the fire lights, the system has to confirm that the flame is actually burning within 3 to 5 seconds. If the flame failed to catch, raw unburned gas would fill the combustion chamber, turning your furnace into a bomb waiting for any stray spark. To prevent this, modern appliances use a clever physics phenomenon called flame rectification. A small metal probe called a flame sensor rod sits directly inside the blue flame. The control board sends alternating current, or AC voltage, into this rod. Because a burning flame contains ionized gas molecules, the flame acts as a natural electrical diode, allowing current to flow in one direction toward the grounded burner plate, but resisting current flowing backward. The control board detects this tiny direct current, or DC microamp signal. If the flame blows out, the ionized path vanishes instantly. The microamp signal drops to 0, and the control board shuts down the gas valve in less than 2 seconds, locking out the system and preventing a catastrophic gas buildup. In older water heaters without electrical power, this safety check is performed by a thermocouple. A thermocouple consists of two dissimilar metals welded together at the tip. When the heat from the pilot flame heats this junction, it generates a microscopic electrical current known as the Seebeck effect, producing roughly 30 millivolts of direct current. That tiny voltage is just strong enough to energize a small electromagnet inside the gas valve, holding the safety plunger open. If the pilot flame blows out, the metal cools down in 30 seconds, the voltage drops to 0, the electromagnet loses its grip, and a mechanical spring slams the gas valve shut, stopping the leak dead in its tracks. Burning natural gas produces heat, water vapor, and carbon dioxide, but it can also produce deadly carbon monoxide if exhaust venting is compromised. In standard atmospheric water heaters, hot exhaust gases naturally rise up through a metal B-vent chimney due to the stack effect, because hot air is less dense than cold air. Modern high-efficiency condensing furnaces extract so much heat from the fire that the exhaust gas cools down significantly, losing its natural buoyancy. These units use a motorized draft inducer fan to mechanically force the cool exhaust fumes out of the house through sealed PVC pipes while draining acidic condensation safely into a drain. Now, while natural gas is piped in through underground city grids, millions of homes rely on liquid propane, or LP gas, stored in exterior high-pressure tanks. Although propane powers similar appliances, its physical properties introduce a completely different set of rules. Natural gas is lighter than air, meaning that if a leak occurs indoors, the gas rises toward the ceiling and can escape through roof vents. Propane, on the other hand, is 1.5 times heavier than air. If a propane leak occurs inside a home, the heavy gas sinks to the floor, rolling along baseboards and pooling in low-lying areas like basements, sump pits, and crawl spaces, creating an invisible explosive lake that can linger for hours. Because propane has nearly 2.5 times the energy density of natural gas and operates at a higher manifold pressure of 11 inches of water column, appliances must be specifically converted with smaller burner orifices and adjusted regulator springs before they can ever burn propane safely. Knowing how your home's gas system works allows you to spot danger and respond instantly during an emergency. If you ever smell that pungent sulfur odor of Mercaptan inside your house, never flip light switches, never turn on appliances, never use a landline phone, and never unplug cords, as the microscopic electrical arc inside switch contacts can trigger an explosion. Instead, evacuate everyone immediately, leave the front door wide open to ventilate, use a wrench to turn the outdoor meter valve tang perpendicular to the pipe if it is safe to do so, and call the gas utility emergency line from a safe distance outside. From the high-pressure main in the street, through the precision reduction of the service regulator, along the heavy black iron and bonded CSST supply lines, past the debris-trapping dirt legs, and through the microamp safety circuits of the electronic gas valve, your home's gas system is a masterclass in mechanical engineering, fluid dynamics, and automated safety. When maintained properly and treated with respect, it safely delivers clean, reliable, and powerful energy to keep your household warm, fed, and comfortable all year round.